So welcome everybody. You see, I don't know if you can see the participant list, but we got a big class. This is a much bigger response than I thought I would even thought I'd get. And so there's like 31 people in the class. And this is just great. Some of you were in one of my technician classes, and I'm glad you stuck with me for the general class as well. Let me just make sure nobody's waiting here. Okay, good. So if you did take the tech class, this is gonna be a little bit different, because in the tech class, I just really bomb through the material and try to get you a license. I mean, that's the whole purpose there. In the general class, I actually do try and teach you a little bit. And, you know, it's not just the answers to questions. And because of that, I want you to really feel free to ask questions. You know, in the tech class, I did kind of blow over some questions just because we had to keep moving to get through the material. But here we have more sessions, and we have more time to talk about the material. So again, like I say, feel free to ask questions. About the test now. The test is actually pretty similar to the tech test, except it's a little bit more difficult, of course. It'll be 35 questions, multiple choice, got to get 26 right. And the tests are all online now. And there's, if you go to this, that's not part of this class. And so you'll have to go to hamtest.org/sessions to take part in the test, or to take a test, sign up and take a test. Oh, good thinking. I need to start recording here. Oh no, I'm already recording. That's good. Yeah, so the recording, I am making a recording. I'm going to put it on my YouTube video, or my YouTube channel, and you'll be able to watch the video. Any questions? Any other questions before we get started?
Yeah, I just want to say the remote testing we did through the group you connected us with, the VEC, was amazing. Like with Zoom and everything, like they were really, really great, Dan. Thank you.
Yeah, I think, did you take it with the W5Y group?
These are the Dallas or the North Texas folks? Yeah.
Yeah. I think those guys really got it down. So that's good to know, because obviously I didn't take the test. Any other questions?
I take it the test is closed book?
Right. Yep. Unfortunately, you know, some of these questions, you know, you all have taken the tech test, and the questions are similar. You know, some of them, it's like just doesn't make sense to not have it open book. I mean, if I didn't go over this material constantly myself, I would be looking up this stuff in a book. You know, it's just, but that's the test system we have. So
I have a question.
Yeah.
On the test, can we have paper and pencil with us this time? Because we weren't allowed to have anything, not a calculator or anything. Can we do that? Because this is difficult math.
Yeah, no, I mean, they should have let you have some scratch paper or something. That doesn't make sense to me, but maybe so.
I was looking at the rules for it a few minutes ago, and not only can you not have paper and pencil, if you want a calculator, you have to use the on-screen calculator on your computer. You can't use a desktop calculator.
Okay, I guess that's the way they do it.
And different testing places might have different rules. I don't know, but that's what I saw so far.
Yeah. Well, so there's two main groups, I think, that are on that hamtest.org/sessions. One is the W5YI group that took the test with, and Christina did. The other one is the Greater Los Angeles Amateur Radio Group, GLAARG.
Can the person with the dog please mute?
Dan, can you mute all the participants?
Well, if I mute everybody, then you can't ask questions. So, but yeah, maybe the dog person could. get the dog out of the room.
Yeah, that dog is setting off my dog too. My dog's barking at him in response. Come on, I'm gonna let him out. Come on.
But so maybe the Great Lake. I'll ask I know the guy at the Greater Los Angeles group. I'll ask him about that.
That is so funny.
Because yeah, I mean, it would be helpful to be able to make some notes or make some calculations. Any other questions?
Oh, good.
All right. Well, I'll get started then, and we're going to follow pretty much the same subject matter as we did with the tech test, and we'll start out with electrical principles first. And I'm going to share my screen here.
Jag behöver mer ljus så jag kan inte läsa här.
Okay.
Please. Bara lite.
Ja.
Han tänder ljuset på sin screen så det kanske räcker.
Okay, so hopefully you can all see this now. And
Not yet.
I
how about
can't
now?
see your blank
Yeah.
whiteboard.
No.
I can see it.
Okay, good. So we're going to start off by talking about reactance. So, in the tech test, we concentrated on Ohm's law, V equals I, E equals I times R, right? Where R was just resistance, but from a resistor, and it was only resistance. It was, sort of everything here was DC, right? We talk about DC circuits mostly. Well, most radio equipment, it works with alternating current. An RF signal is an alternating current. And so we have to talk about reactance. Reactance is the resistance provided by some components to alternating currents. And the thing about reactance is that it's frequency dependent. So we have inductors here. These are inductors, right? This is actually the same diagram I had from the tech test. And for inductors, the reactance, and we use the letter X for reactance, the reactance is 2 pi FL. So as frequency goes up, the reactance goes up. The capacitive reactance, X sub C, is 1 over 2 pi FC. And so as the frequency goes up, the reactance goes down. So these are sort of very complementary. So some of the questions on the test. What is reactance? Opposition to the flow of alternating current caused by capacitance or inductance. Question, what unit is used to measure reactance? Answer, ohm. So we use the same unit of measurement as the ohm. Question, which of the following causes opposition to the flow of alternating current in an inductor? Answer, reactance. Question, which of the following causes opposition to the flow of alternating current in a capacitor? Answer, reactance. So those are the two things you have to remember for the general class test. Now, I sort of hinted at this in the tech class, but I'll hit at it again here. So we're not talking anything about phase or anything here, but you can almost see from the equations that these two are sort of opposite one another. And in fact, they do shift the phase of a signal entering them, and they shift them in opposite directions. So what happens when X sub L equals X sub C? Well, if X sub L equals X sub C and they're sort of opposites one another, they cancel each other out. And then all you get is the resistance in a circuit. So if you had a coil, and a capacitor, and a resistor, at some frequency, F, X sub L is going to be equal to X sub C. And this is going to seem like an open circuit or a short circuit. So there's going to be no reactance at all, and all you have is the resistance. This frequency is called the resonant frequency. And this isn't on the test, but I'm just sort of, you know, sort of showing you what can happen here. And that's how we get, you know, oscillators to oscillate and radios to receive certain signals is by manipulating the X sub L and X sub C such that we get a frequency. You know, we do that to get a frequency. So like I said, as frequency goes up, X sub L goes up. Question, how does an inductor react to AC? Answer, as the frequency of the applied AC increases, the reactance increases. How does a capacitor react to AC? As the frequency of the applied AC increases, the reactance decreases. So that's all there.
That's a good for here. We each got 3.
So now let's talk a little bit about impedance. We got reactance. Now what is impedance? Well, impedance is the complex combination of reactance and a resistance. So I'll draw this circuit again. So at anything but the resonant frequency, we'll have some net reactance here, right? And this reactance will combine with this resistance to give us impedance. So it's without getting into the real long discussion, which you don't have to know till the extra class test anyway. It's the combination of those two, but it's still a resistance or an opposition to the flow of alternating current. So question, what is impedance? Answer, the opposition to the flow of current in an AC circuit. And that's really what you have in an antenna too, right? You know, we say that it has a certain feed point impedance. Well, it's and usually they like to design it so it's about 50 ohms, right? Because everything's 50 ohms in ham radio. And so that's sort of the important point here, is that impedance is the combination of reactance and resistance, and it's an opposition to, it's still opposition to the flow of AC current. And it's different from reactance, because reactance is sort of a pure reactance, right? This is a combination of reactance and resistance. That's impedance. Why is this important? Well, it's important because you want the source impedance to match the load impedance, and by that, and so I this is sort of a theoretical representation of this, but you have this situation in ham radio where you have a transceiver and an antenna. In this case, the source impedance is here in the radio, and the load impedance is the antenna. So this is the Z sub L, and this is the Z sub S. And I should have mentioned, impedance, we use the letter Z for impedance. So why do you want Z sub S to equal Z sub L? That's so you can transfer the most power from the source to the load. So let's think about this a little bit. So if Z sub S equals 50, we'll just take this as an example. is 50 ohms. Decibel equals 50 ohms. And let's say the source voltage here is 100 volts, just for kicks, just because it all works out easy. Well, the current I flowing through there will be what? It'll be 100 divided by 100, V over R, or 1 amp, right? And the power delivered to the load will be, so P equals I squared R equals 1 amp times 50 ohms, or 50 watts, right? Now, let's take an example where Decibel isn't 50 ohms. So if Decibel were 100 ohms, then I would be equal to 100 over 150, or about 0.67 ohms. And then the power would be equal to I squared over R. That'll be, or I squared times R, sorry. So I squared is going to be about 0.44 times 100, or only 44 watts. So you see, matching the source impedance to the load impedance allows you to transfer the most power from the source to the load. And it's similar if you actually it's worse. If this was 100 ohms and this was 50 ohms, it's even worse. It works out to about half this actually, or about 22 watts, 22 to 23 watts. So that's why you really want the source impedance to match the load impedance, because that'll transfer the most power. And in this case, if you got a transceiver here, you'll transfer the most power from your transceiver to the antenna, and you'll radiate the most power out of the antenna. So that's the question here. What happens when the impedance of an electrical load is equal to the output impedance of a power source, assuming both impedances are resistive? And that's what we got here, right? We got two resistive. Answer: the source can deliver the maximum power to the load. And that's why we go to such great lengths in ham radio to match our antennas to our radios, right? So we can transfer deliver the most power to the antenna. And how do we do that? Well, if you remember the tech test, there's a variety of ways to do that, right? We can use a transformer. This is an example of a transformer here. Whoops. No, that'll work. This is a transformer here. A 4-to-1 balun is a transformer. Or we can use an LC network. That's what this is, made up of L's and C's. And in both cases here, we're doing what's called impedance matching. The input impedance, we're trying to match the input impedance to the output impedance. Or like in this case, ZL here, right? So question: what is one reason to use an impedance matching transformer? Answer: to maximize the transfer of power. Question: which of the following devices can be used for impedance matching at radio frequencies? Answer: a transformer. That's what a balun is. In this case, it's a 4-to-1 balun because these two windings are the same number of windings. If this was this was a 3-to-1, and it goes by the square of the number of turns. So if we had a ratio of 3-to-1 here, we'd have a 9-to-1 balun. And sometimes you'll see these on end-fed antennas. So transformer, a pi network, that's what that's what this is. An LC network is a type of pi network. Or a length of transmission line. I didn't draw that here, but that's the answer to this question. Which of the following devices can be used for impedance matching at radio frequencies? Answer, all these choices are correct. Question, which of the following describes one method of impedance matching between two AC circuits? Answer, insert an LC network between the two circuits. So in this case, we're matching the output impedance of a transformer or amplifier to an antenna. You can think of this as one of the circuits, and then the antenna actually is the other circuit. Any questions about this? The important thing to remember here is that when you're impedance matching, you're trying to, again, maximize the transfer of power. That's the basic principle here, and we do that in any number of ways. All right. I got these a little bit out of order here. What happened? All right. So now we're going to talk about AC parameters, sine wave parameters. Why is this important? Well, when we calculate power, let's say the power of an RF signal, we use what's called the RMS voltage. The RMS voltage is kind of like the effective voltage of an AC signal. And you can see the relationships here. So let's just take the 120 volts AC you get out of the wall. Well, if you actually put an oscilloscope on it, you 120 volts is the RMS value. So if you put it on a scope, you'd actually see a higher voltage than the 120 volts AC. In fact, this peak voltage here is the RMS voltage times 1.414, which is the square root of 2. That's where you get root from, because it's the square root of, or is the square root of 2. So that's the peak voltage. The peak to peak voltage is twice the peak voltage, because it's from the most positive peak to the most negative peak. So it's twice the peak voltage. And like I say, the reason you need to know this is that some of the questions are worded this way. And you have to sort of know these values. So question, what value of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value? Answer, the RMS voltage. So, if you plug the resistor into the wall, which you probably wouldn't, but if you did, and you could, right? You could. Not that I recommend it, but it might be amusing. If you put a let's say a 1200 ohm resistor into the wall socket, yeah, you'd get about 100 milliamps of current, which is not a lot. Just be careful. But what's the point of that? Well, the point is that this resistor would heat up just as much as if you put 120 volts DC into it as well. You know, if you connected it across a 120 volt DC battery or DC power supply, this resistor would dissipate the same amount of power. It would get just as hot. So that's the whole idea of the RMS voltage. That's why I sometimes think of it as the effective value of the voltage. Even though, like I said, if you put a scope across here, you would find that the maximum voltage is like 179 volts. Or 170 volts.
Is the 1414, is there something exceptional about kind of like that ratio? Like if I were to go like 208 volts or some other voltage, would I see the same number, or is it proportional?
You'd see the same ratio. No, you'd see the same ratio. So the peak voltage of 120 volts AC is about 170 volts, right? So this value here would be 170 volts. If you had 240 volts, well, you'd have 340 volts peak voltage. See what I'm saying?
Yeah.
Okay, so question, what is the RMS voltage of a sine wave with a value of 17 volts peak? So if the peak value is the VRMS times 1.414, the RMS voltage is the peak voltage divided by 1.414, right?
Mm-hmm.
Or VP times 0.707. So question, what is the RMS voltage of a sine wave with a value of 17 volts? 17 times 0.707 is about 12 volts. So they conveniently chose that value so it comes out even. Question, what is the peak? Here's the well, sort of a similar question to the one we just covered. Question, what is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? So BP equals 120 times 1.414. That's it's almost 170. It's actually 169.7. Because the peak-to-peak voltage is twice that. That means VPP equals 2 times 169.7 or 339.4 volts. All right.
I'm sorry for interrupting, but this is hard enough for me as it is. Is there any way that everybody would please mute? Somebody's got an annoying radio or television on in the background, and it makes it very hard to concentrate on what Dan is saying. Would everybody please just mute until you're ready to say something? I'm getting a thumbs up, so everybody else is getting annoyed with it too.
I agree. It's very distracting.
Dan, what did you multiply by 2 again? Is it to find the peak to peak?
Uh-oh, Dan.
Dan, you're muted.
No.
All right. There you go. The peak voltage is 120 volts, right? Times 1.414, because it's RMS times 1. That's 169.7. That's this value here. That's the peak voltage. The peak to peak voltage is twice that. So 2 times 169.7 is 339.4. That makes
Perfect.
sense?
Yes, that answered the question.
All right. So the reason this is important, where's my layer here? Since I got this out of order, oops, not that one. I can't find the layer I'm drawing on here. Well, that's weird. Oh, I must be drawing right on the layer. Oh, that's not good. Oh well, I'll just continue with this. No, I'm not. What I'm trying to do here is get rid of these calculations. Here. So the reason this is important is because when you calculate power, you have to use the RMS voltage. So you remember we said P equals E times I, right? Well, in an AC circuit, this is ERMS times I. And actually that's IRMS too, but that's what we'll go with here. And you know all the other equations apply too. So it's B. Actually, I should use a B here. This is really the kind of the confusing thing. So it's V squared RMS times, or let's see. Make sure I get this right. V squared RMS over R, and then I squared RMS over R. So there's some questions on the test about calculating AC power. Question: how many watts of electrical power are used if 400 volts DC is supplied to an 800 ohm load? Right. So P equals V squared over R, and we're going to use. Well, this is a DC question, so it's just a straight calculation. 400 squared over 800, 160,000 over 800, and that's equal to 200 watts. Oh, these are all DC. This first batch here. Sorry about that. Question: how many watts of electrical power are used by a 12-volt DC light bulb that draws 2 amperes? Well, that's just P equals V times I equals 12 times 0.2 or 2.4 watts. Question: and these are the same equations we use in the tech test. Question: how many watts are dissipated when a current of 7 milliamperes flows through a 1250 ohm resistance? Well, this case we'll calculate P equals I squared. Actually, it's I squared times R. I squared times R equals 0.007, right? Because that's 7 milliamperes squared times 1250. And if you put that in your calculator, you'll see that you get to be about 0.061 watts or 61 milliwatts. So these three questions are just DC power, and you should know how to do that already. But the next set of questions here are what's more important. This is where we have to use this RMS business. Question: what would the RMS voltage across the 50 ohm dummy load dissipating 1200 watts be? And so to get this, the equation goes, it's like power equals V squared RMS over R. Wait, yeah, V squared RMS over R. And so then V squared equals P times R. And in this case, the P is 50. Or wait, the resistance is 50. So we got 1200 times 50, or 60,000. And to get the VRMS, you have to take the square root of that. And that's about 245 volts. So like I said, this is, we in a power calculation, you have to use the V squared RMS. So you have to know that value. In this question, they actually gave that to you, so the calculation is a little bit easier here. So there's also a concept here of peak, since we're talking about power, there's a concept here called peak envelope power, PEP. Now, if you remember when we talked about phone, right? Phone or AM or single sideband signals, the power, since the amplitude is constantly changing, that's why we call it amplitude modulation. The power actually is going to be constantly changing. And the peak envelope power, and it'll change with the amount of audio power that you're modulating the signal with. So if so the power is always changing. Well, that's not very good drawing there, but so the peak envelope power will be the maximum point of this signal. So this is the peak power. If you had a Morse code signal, a CW signal, you wouldn't have this kind of variation. It would be the same all the way across. So here's the question about that. What is the ratio of peak envelope power to average power for an unmodulated carrier? Well, it's 1.00 because the average power is equal to the peak power because you're always generating the maximum power. Question: what is the output PEP of an unmodulated carrier if an average reading watt meter connected to the transmitter output indicates 1060 watts? Answer: 1060 watts, because the ratio is 1:1. Question: what is the output PEP, peak envelope power, from a transmitter if an oscilloscope, this is the tricky one, if an oscilloscope measures 200 volts peak to peak across the 50 ohm dummy load connected to the transmitter output? So you have to, first off, you have to calculate the RMS voltage. and you have to know what the peak voltage is. Well, they tell you the peak to peak voltage is 200 volts. So the peak voltage is 100 volts, right? Then to get the RMS value, VRMS, equals this times 0.707. So that's 70.7 volts. And then that's what you use in the calculation. P equals V RMS squared times the R, which is 50 volts. So 70.7 squared times 50. Or divided by 50, I'm sorry. And they chose this to work out quite easy because 70.7 squared is 5,000. Divided by 50, you get 100 watts. But the trick part of this question is they give you the peak to peak voltage of 200 volts. And you have to then divide it by 2 to get the peak voltage, and then multiply it by 0.707 to get the RMS voltage. And then that's what you use in the power calculation. All right, any question about that? Let's do the next one then. Question, what is the output PEP from a transmitter if an oscilloscope measures 500 volts peak to peak across the 50 ohm resistive load connected to the transmitter output? Well, so you do the same thing, right? VPP equals, what is it here? 500 volts this time. Meaning the peak voltage is 250 volts. The RMS equals 250 times 0.707, or 176.75 volts. And then P equals V RMS squared divided by R. And if you throw that in your calculator, divided by R. If you put that into the calculator, you'll get an answer of 625 watts. Most questions I get from the general class study guide is about this question. And the biggest thing they forget to do is to change peak to peak voltage to peak voltage. And you know, the other thing that's kind of neat about this, if you think about it, if you did have an oscilloscope, you could measure the output voltage of your transmitter. And at 100 watts, that voltage is only going to be, what, 50 volts, right? And at 625 watts, it's 250 volts. So as long as your oscilloscope could measure that much voltage, yes, you know, assuming you had a dummy load, a 50 ohm dummy load connected to the output of the transmitter, then, you know, you could look at your transmitter and see how well it's working. You could measure the output power just by measuring the voltage. Throw that into these equations, and you can actually measure the output power of your transmitter. So all kind of fun things you can do. Any questions about that? All right. Let's take a look at decibels. So in the tech test, all we did with decibels was all you had to do was remember 3, 6, and 10, right? 3 was the ratio of 2 to 1, power ratio of 2 to 1. 6 was a power ratio of 4 to 1. And 10 dB was a power ratio of 10 to 1. Well, here we can actually calculate them. This is the equation to calculate decibels from a power ratio. And there's some question about this, how to do this. So actually, the first question is the same as the tech test. What decibel change represents a factor of 2 increase or decrease in power? Answer, approximately 3 dB. So let's actually do this. So if P2 over P1 equals 2, this would be 10 times log 10 of 2. And if you punch that into your calculator, you'll see that's log 10 of 2 is 0.301. So it's 10 times 0.301 or 3.01 dB. So that's where the number 3 came from in the tech test, right? This is the log 10 of the power ratio times 10. Question, what percent of power loss would result from a transmission line loss of 1 dB? So this is where it gets a little bit trickier. So what you have to do is use this equation and then do a little manipulation on it. So in this case, P2 over P1, P2 over P1 is equal 10 to the A and dB divided by 10 power. Well, the A is 1, so you get P2 over P1 equals 10 to the minus 0.1 power. And if you throw that into your calculator again, this is why you need a calculator for the general class test. This would be 0.794. So the P2, which is the output power, you know, if you added this length of coax, and so P1 would be here, P2 would be here, and so you'd have some loss. So P2 is 0.794 or 79.4%, right? The loss would be 1 minus 79.4% or 20.6%. So that's the amount of loss you'd get in that piece of feed line. Does that make sense? So you have to be able to, you have to sort of know this equation and then be able to manipulate it into this form. Then you can do the calculation. All right, I guess no question. I'm going to continue on here. So now we'll talk about components in series and in parallel. You know, we talked about this before, but now we'll talk about it in a little bit more depth. So these are the two circuits we had in the tech test. And what you can see here is that the total resistance. So in the case of the series case, the total resistance is R1 plus R2. And that's the sort of the basis of these questions. So question, which of the following components increases the total resistance of a resistor? Now I hate the wording of this question. I tried to get them to change it, but no, they never listen to me. But the answer is a series resistor. So if you had a resistor and you wanted to increase the total resistance, you add another resistor. That's the idea here. So a series resistor would increase the total resistance of the circuit. They should have changed it to circuit. Question, if 3 equal value resistors in series produce 450 ohms, what is the value of each resistor? Well, so in this case, 450 is equal to 3 times X, right? It's, you know, because you've got 3 resistors, you just add them up, R1 plus R2 plus R3. And 450 over 3 is equal to 150. So that's 150 ohms. If you put 350 ohm resistors in series, you get a total resistance of 450 ohms. When you have resistors in parallel, however, it actually decreases the effective resistance. And the reason for that is that you have multiple current paths. So by adding a resistor in parallel, you increase the total current that you draw from the battery. That makes it look like there's less resistance out there. And the equation is R total equals 1 over R1 plus 1 over R2 ad infinitum. And when the R's are equal to one another, you get the effective resistance, the total resistance, is just the value of a single resistor divided by the number of resistors. So the question, what is the total resistance of 3 100 ohm resistors in parallel? Well, if you have 3 of them, 100 divided by 3 is 33.3 ohms. Question, what is the total resistance of a 10 ohm, a 20 ohm, and a 50 ohm resistor connected in parallel? Well, so for this one, you have to use the equation. So R total equals 1 over 50 plus 1 over 20. So make sure I get it right. 1 over 20 plus 1 over 10. That's 1 over 0.17. If you do the math. And that's, if you do that division, you get 5.9 ohms. And I skipped over a question previously, and we'll go back to it here. Question, how does the total current relate to the individual currents in each branch of a purely resistive parallel circuit? Answer, it equals the sum of the currents through each branch. So, I mean, that's what we're doing here, right? We're doing, this is the reason this works. So, I total, this is I1 and I2, I total equals I1 plus I2. In engineering, we call this Kirchhoff's current law. It's sort of like a conservation of current, right? You get the same amount of current is going to enter the battery that left it. And if it splits into different branches, well, then the sum of the currents in each of the branches, the sum of those currents has to equal the total current. You know, the amount of current going into this node has to equal the current leaving the node. It doesn't just disappear. So that's the idea here. Any questions about that? Okay, so then there's questions about inductors and capacitors and how that works. And the way it works is for inductors, it's the same as for resistors. So inductors in series will add with one another, and in parallel, they'll combine with that funky equation. So question, which of the following components should be added to an inductor to increase the inductance? Answer, an inductor in series. So you could, you know, just, whoops. So if this was L1 and L2 in series, the total inductance is L1 plus L2. And in parallel, L total equals 1 over L1 plus 1 over L2. Oop. Capacitors work differently though. Capacitors in parallel actually add up. So if you had C1 and C2, C total equals C1 plus C2. And capacitors in series you have to use that equation, 1 over C1 plus 1 over C2. And there's a bunch of different questions about that. Question, what is the inductance of a 20 millihenry inductor connected in series with a 50 millihenry inductance? Answer, 70 millihenries. So 50 plus 20 equals 70. Question, what is the inductance of 3 10 millihenry inductors connected in parallel? Well, it's this. That's almost the same question as the resistors in parallel. If you have 10 millihenries in parallel, and there's 3 of them, 10 millihenries divided by 3 is 3.33 millihenries. Oops. 3.33 millihenries. And like I said, capacitors are sort of the opposite. So question, which of the following components should be added to a capacitor to increase the capacitance? Answer, a capacitor in parallel. Question, what is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? Well, you'd use this equation here. You get, I'll go up here, 1 over 50, 20 plus 1 over 50 equals 1 over 0.07. And that works out to about 14.3 microfarads. Question, what is the capacitance of three 100 microfarad capacitors connected in series? Answer, 33.3. So here, again, we're connecting them in series, but since they're three equal values, it'll be the value 100 microfarads divided by 3, and that's 33.3. Oops. 33.3 microfarads. Oops. Any questions about this? Just remember, inductors combine the same way that resistors do, and capacitors combine in the opposite way. And then there's a few questions here about about unit conversion. This is the same idea that we did in the tech test. What is the value of nanofarads of a 22,000 picofarad capacitor? Answer, 22. That's because there's 1,000 picofarads in a nanofarad. What is the value in microfarads of a 4,700 nanofarad capacitor? Answer, 4.7. That's 1,000 nanofarads in a microfarad. So you divide by 1,000. Then this question, oops. Let's get rid of this. This one's going to take a little bit of a calculation. Question, what is the equivalent capacitance of two 500 nanofarad capacitors and one 750 picofarad capacitor connected in parallel? So this is the circuit. We have three capacitors connected in parallel. These are both 5 nanofarads. And this is 750 picofarads. Well, so these two 5 nanofarad capacitors will combine in series to be 10 nanofarads. 750 picofarads plus, because it's in parallel, so we're going to add that, is 0.75 nanofarads. So the answer is 10.75 nanofarads. All right, any questions about that? Just have a short bit here, then we'll take a break. Talk about inductors next. So, get rid of this. Inductors exhibit a property called mutual inductance. And what that means is that a current in one inductor may cause a current to be induced in a nearby inductor. Because remember what happens here. When you send a current through an inductor, you generate a magnetic field around it, right? No, that's not a very good drawing. Sorry about that. But that magnetic field when it cuts through the winding of the second inductor, it'll cause a current to flow in that inductor. Maybe it's the other way, I forget. But it'll cause that to happen. It's called mutual inductance. So question, what causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary winding? Answer, mutual inductance. So if this was a transformer, we'd call this the primary winding, because that's where we're actually generating the current, sending the current into, and this is where we're getting the current from. So this is the secondary winding. Now, the secondary voltage and the primary voltage are related, of course. So if you had the same amount of windings in both, you'd get the same amount of voltage across the secondary that you would to the primary. And of course, that's not usually what you want. Usually you want to actually transform the voltage. Although sometimes you do want one-to-one if you're just using it as a quote-unquote isolation transformer, because what you're doing there is isolating this circuit from this circuit. But the secondary voltage is related to the primary voltage by the ratio of turns, N1 to N2. Or actually N2 to N1, sorry about that. So question, what is the RMS voltage across a 500 turn secondary winding in a transformer if the 2250 turn primary is connected to 120 volts AC? So use this equation, 120 volts times 500, because that's the number of turns in the secondary, divided by 2250. And if you put that in your calculator, you'll get 26.7 volts. So there's fewer turns in the secondary than the primary, so you get a lower voltage. If you had more turns in the secondary, you'd get a higher voltage. Sometimes we call this a step-down transformer. Question, what happens if a signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary winding? So if you put the voltage here on the secondary winding, what would happen? Well, if it's a 4-to-1 step-down transformer, you'd expect N2 over N1 to be 1 to 4. But if you do it in reverse, then you get you flip those two and you get a 4-to-1 increase. So the answer to this question is the output voltage is multiplied by 4. Because now the secondary is really the primary and vice versa. So the voltage ratio will be N1 over N2, and that will be equal to 4. Again, this is a stupid question. You really would never want to do this. And why wouldn't you want to do it? Because if you're stepping down the voltage, then you use a certain conductor's size of conductor to handle the current you're going to generate, right? So question, why is the conductor of the primary winding of many voltage step-up transformers larger in diameter than the conductor of the secondary winding? Answer, to accommodate the higher current of the primary. So step-up basically the idea is whatever power you put in, you get out, right? You're never going to get more power out than you put in. So if the voltage is lower on the primary, or is higher on the, let's see, conductor of the primary. So if this secondary winding, if you have a step-up transformer, then the voltage will be higher, meaning the current will be lower. And so you can use a lower gauge wire, smaller gauge wire in the secondary. And so you have a higher current in the primary, so you use a larger gauge wire in the primary. That's the idea of this question. If you do it in reverse, then you've got the smaller gauge wire here, and it's just not a good idea to do that because you have a higher current. So question, why is the conductor of the primary winding of many voltage step-up transformers larger in diameter than the conductor of the secondary winding? Answer, to accommodate the higher current of the primary. So sometimes we use transformers to transform impedance. And when we do that, we have to use the square of the impedances. So the turns ratio, N2 over N1, will be equal to the square root of the output impedance to the input impedance. That's when we're using a transformer for impedance matching. So question, what is the turns ratio of a transformer used to match an audio amplifier having a 600 ohm output impedance to a speaker having 4 ohm input impedance? So the turns ratio is this equation. In this case, that's square root of 600 over 4. And again, if you run that through your calculator, it's the square root of 150 or 12.2. So in this case, your secondary winding will have 12.2 times the number of turns as the primary winding. Any questions about that? All right, let's take a short break. I know there's a lot of material here, and let's take a 5-minute break, then we'll talk about circuit components. This is a very short chapter, so we'll be able to get through it real quickly. Don't throw your laptop, Leo. You know what? If you break the laptop, you can't attend the next set of classes. Some of these questions really kind of bug me, actually, because some of them are just like out of left field. and to try to explain them in a study guide or in a class like this is just really kind of hard. I got these all out of whack here. This is actually the first time I tried teaching this general class online, so I hope you'll stick with me on this. And feel free to give me, email me with any feedback you have about this too. So, you know, if you want to do this offline, that's fine too.
Could have fooled me. It seemed like you'd done this a lot.
Well, so I've taught this general class, well, maybe at least 3 or 4 times, but never online. That's online's different. And well, the only reason it seems like I do it a lot is because I, write these study guides, and it's like I've been over these questions over and over and over and over for the last 15 years. Well, maybe not that long, 12 years. So that's the story there. Like when we get to the part about digital logic, that's really the worst, because the worst section in the general class study guide. The reason for that is, I took this stuff in college, right? I have an electrical engineering degree. We did a whole semester on just digital logic. And on the general class test, there's like 5 questions, or, so it's like, I mean, there's no way to almost to teach the theory behind it. At least with the AC stuff, I can show you the peak to peak voltage and explain how that all works. It's not that complicated, but digital logic is very complicated. And, it's just tough to do. All right, so we'll talk about, the next up is, share my screen again, hang on. And I can't see you guys when I share my screen, because I got the whole screen here, so you can make faces at me and I won't see it. So next we're going to talk about circuit components, and actually some more practical things about components. Resistors are like the most common type of components. I mean, I think if you added them up, there would be more resistors by a big margin than any other type of component in electronic circuitry. And there's all different kinds of resistors, but unfortunately, they only ask one question, and that's about wire wound resistors. Wire wound resistors are used a lot in precision electronic instrumentation. And the reason for that is we can make the resistance value very precise with a wire wound resistor. And we just don't get that with most other resistors. If you looked at the tolerance of even newer surface mount devices, some of them are like 5% tolerance, or 10%, sometimes more. Well, what does that mean? That means if you bought a 100 ohm resistor and you bought a 5% resistor, they're only guaranteeing that the resistance value will be somewhere between 105 ohms and 95 ohms. But with wire wound resistors, we're talking about 0.1% tolerance, sometimes even better than that. The problem with wire, so that's good, right? I mean, that makes the circuit, we talked about Ohm's law and all this stuff. Well, when we do those calculations, we use the nominal value in those problems, but actually it could be anywhere between here. So, I mean, you never really know. But with wire wound resistors, you get pretty accurate. So that's good, right? Well, it is good, but not in all cases. And why is that? So this is sort of a cutout view of a wire wound resistor. And you see, they take this piece of wire, which they know the resistance, they call it resistivity, which is the resistance per unit length. And they put that amount of length there to get whatever value they want. Well, they can do that very precisely. But what are they doing here? They're making an inductor here, right? And that's what it is. You got a coil of wire, that's an inductor. So it has an inherent inductance. And that inductance can cause an RF circuit to malfunction, because now, instead of just a simple resistor in your circuit, you got a resistor and a resistor and an inductor, effectively. So question, which of the following is a reason not to use wire wound resistors in an RF circuit? Answer, the resistor's inductance could make circuit performance unpredictable. That's to say the least. It could cause it to malfunction in the worst case. So let's talk about capacitors now. Just like with resistors, you can get a wide variety of different types of capacitors. And, remember, we've got some capacitors measured in picofarads, all the way up to capacitors measured in microfarads. And, that's a factor of 1 million between the two. So we have a very wide range of capacitance that you deal with in electronic circuits. Perhaps the most common type is this ceramic capacitor. And we call it a ceramic capacitor because it not only has a ceramic outer coating, usually the dielectric in there, and if you looked at it from the side, you'd see this ceramic dielectric, and then a metal. Oops, that's not drawn so well, is it? These metal layers, and then onto that you got the leads soldered. But this is ceramic here, and it's that separation that gives you the capacitance, right? Probably the largest number of capacitors are ceramic capacitors. And why is that? Well, one reason is they're cheap. So question, which of the following is an advantage of ceramic capacitors as compared to other types of capacitors? Answer, comparatively low cost. The other type of capacitor, common type of capacitor, is called the electrolytic capacitor. This is a typical electrolytic capacitor. These offer very high capacitances. This one here, this 1.103 is the value, and that's a 0.01 microfarad capacitor. Okay, this capacitor here, which is about they're similar in size. This one is 2,200 microfarads, so it's like 200,000 times the value of this, 200,000 times the capacitance. Well, so how does that get to that? Well, for one thing, this thing is rated at 3 kilovolts, 3,000 volts. You can put 3,000 volts across this capacitor. This one's rated for 16 volts. not quite the same. Not quite the same value. So you can't really put too much voltage across some of these electrolytic capacitors. But they're used in different applications, so that's okay. Question, which of the following is an advantage of an electrolytic capacitor? Answer, high capacitance for a given volume. And you notice another thing about electrolytic capacitors is that they're polarized, meaning you this is you have to connect this so that this lead marked by this stripe is negative with respect to the voltage on this lead. So generally, you connect this lead to ground and then this to whatever voltage you've got on the circuit. So it's polarized. They're polarized capacitors. One time we were doing a club construction project, and it had a electrolytic capacitor in it. So we all put the kits together and we all got them working. And one of the guys, when he put the voltage on it, you heard this big pop. And what had happened was he had gotten his capacitor in backwards and it actually exploded. And we all had a good laugh because the guy who did this was like one of our most experienced members. And the fact that he got it in backwards, we all had a good laugh at his expense. But question, why is the polarity of applied, but it could have been dangerous actually, because this thing did explode, like I say. Question, why is the polarity of applied voltages important for polarized capacitors? Answer, all of these choices are correct. Incorrect polarity can cause the capacitor to short circuit. Reverse voltages, meaning incorrect polarity, can destroy the dielectric layer of an electrolytic capacitor and cause it to fail. Answer, the capacitor could overheat and explode, which is what happened in this case. And we still kid him about it. This happened years ago already, but we still joke about it. So those are probably the two most common types of capacitors in electronic circuits. Any questions about capacitors? One thing about electrolytics, if you may have heard of the bulging capacitor problem in some electronic equipment. That's because they used cheap electrolytic capacitors, which eventually failed, and they actually started bulging. And so if you look inside your equipment at some point and you see the capacitor isn't nice and straight like this, you know that you probably are going to end up replacing that capacitor sooner or later, because bad capacitors will bulge out. So if you looked at it like from the side, they actually bulge out. All right, next thing we'll talk about is toroids, or toroidal inductors. These have gotten to be popular in amateur radio because a number of reasons. You can make them very small for a given inductance, and they're inexpensive. They can be inexpensive that way. One of the things that if you buy a kit with a lot of these toroids in them, they can be kind of a pain to wind because you end up winding your own. Usually the ones we use in amateur radio don't have quite so many windings. I couldn't find one that didn't have so many windings. This is more of a choke. Oops. This is more of a ferrite used as a choke, and we'll talk a little bit more about that. But the other thing about these things is this is use enameled wire. Well, but to actually put it into a circuit board, you have to somehow get that enamel off the wire, that enamel insulation. And you can, sometimes you do it with a, people do it with an X-Acto knife. That's a real pain. And what you really need is some kind of solder to be able to burn that insulation off. That's what I use. I have a little thing that I can actually dip it in a little bit of solder and it burns the insulation off. But not all the enamel will burn like that. That's another problem. Anyway, we use a lot of these in amateur radio. If you crack open a piece of amateur radio equipment, you'll undoubtedly find some of these toroidal inductors in there. And the common name for them is just toroids. So question, what is an advantage of using a ferrite core toroidal inductor? Answer, all of these choices are correct. Large values of inductance may be obtained. The magnetic properties of the core may be optimized for a specific range of frequencies. Most of the magnetic field is contained in the core. And that's a good thing, right? Because this mutual inductance we talked about, 15, 20 minutes ago. If you have a number of these, if you use the toroidal inductors, that restricts the magnetic field closer to the inductor, so mutual inductance is less of a problem. So you might ask, well, how does the magnetic property of the core, how can you optimize that for the specific range of frequencies? Well, I'm sorry about the small size of this. I thought it would be a little bit bigger. But this shows a number of different what are called mixes, and these actually are different types of core material. And you'll see that the frequency range, it specifies the frequency range for each mix. So they actually will change the characteristics of these toroidal cores, and you use a different type of core, a different mix they call it, depending on what your application is. And I can send you this chart if you want, or it's on the internet. That's where I got it from. So question, what determines the performance of a ferrite core at different frequencies? Answer, the composition or mix of materials used. And again, that works. If you're using it as a choke, well, you want one type of core. If you're using it as a balun or a transformer, you might want a different mix. If you're using it at 160 meters, you might want to use one mix. If you're using it up at VHF frequencies, you might want to use a different type of mix. Question, how does the ferrite, so like I say, one of the ways we use it is as a choke. This is probably a choke. And what they mean by choke is that it chokes off RF currents. So you see, we have a lot of windings on there. That means the inductance is pretty high, meaning the inductive reactance will be high at higher frequencies, right? Because the inductive reactance increases as the frequency increases, and it increases with the inductance too, right? Decibel equals 2 pi FL. So as the inductance as the number of turns increases, the inductance increases, and your reactance will increase. So that's called a choke, when you use a lot of turns to produce a high inductance. And we use these a lot, in ham radio. I mean, because a lot of times we want to, prevent RF currents from flowing. And it not only works in a toroid like this, but you remember we talked about ferrite chokes in the tech test. They were snap-on ferrites, right? So you have something like this, and you put a wire in here and snap it over, right? Well, even though you're not winding the wire around the core like you're doing here, you still get some of that effect. You still get some of that choking effect. That ferrite will prevent RF currents from flowing on the shield of that cable. And so that's the question here. How does a ferrite bead or core reduce common mode RF current on the shield of a coaxial cable? Answer: by creating an impedance in the current's path. So what you're doing when if you have a coax here, right? And here's the shield, and here's the center conductor, right? What you're doing when you put that ferrite core on there is you're actually, in effect, injecting or creating an inductor on that shield. And that's going to prevent RF currents from flowing. It's actually ferrite material in here. And then, like I said, there's these crazy questions. Question: what happens when an inductor is operated above its self-resonant frequency? So the question is, what is the self-resonant frequency? Well, so we got an inductor here, right? Well, you see how it's wound around the core. Well, you actually get a little bit of capacitance between the windings. And in effect, what you get then is a capacitance across the inductor. Well, remember what I said about resonant frequency. The resonant frequency occurs when X sub L equals X sub C. Because if you got a C, then you got an X sub C, right? Well, the resonant frequency of this circuit is called the self-resonant frequency. And what happens when you try and operate an inductor above that frequency is that in effect, it becomes a capacitor and not an inductor. Because what happens? As the frequency goes up, this X sub L increases, X sub C decreases. So the current isn't going to flow through the inductor, it's going to flow through the capacitor. So the inductor actually becomes a capacitor. It's crazy, but that's kind of how it works. Any questions about that? I've never really run into this myself. It seems to me that you'd have to be pretty high in frequency because the capacitance is going to be pretty low. But it happens, I guess. All right. Diodes. Let's talk about diodes. There's a couple of diode questions. One of the big things about one of the big things about a diode is its forward voltage drop. So, you know, we like to think of a diode as like a perfect, I don't know, switch, if you will. You know, when the voltage is positive with respect to on the cathode with respect to the anode. Oops. On the anode with respect to the cathode, it's when it's positive, you know, you get current flow, right? And you like to think that this sort of becomes a short circuit, but it doesn't. There's actually a voltage drop across here. And in most diodes that you have, that you use and see in amateur radio equipment, are silicon diodes. And for silicon diodes, that voltage drop is 0.7 volts. So it's almost like a resistor in a way. And in fact, sometimes you'll see diodes being used to drop voltage. by 0.7 volts if it's a silicon diode. In some amateur radio equipment, they still use germanium diodes. Germanium diodes have a forward voltage drop of 0.3 volts. And the reason you use them is because that voltage drop is less, meaning if you're using it like in a detector circuit or something, you can get a little bit more sensitivity if you use a germanium diode. So question, what is the approximate junction threshold voltage of a conventional silicon diode? Answer, 0.7 volts. What is the approximate junction threshold voltage of a germanium diode? Answer, 0.3 volts. These are getting really hard to get, and these are the ones diodes that are mostly used in crystal radios, for that same reason, because they drop less voltage. But they're getting hard to get. You almost can't find them anymore. Questions about diodes? All right, let's talk about MOSFETs. So what are the types of there's all kinds of different types of transistors. And one of the most common types is the metal oxide field effect transistor. This is the kind of transistor used in most digital logic integrated circuits. And they're also used a lot in now in as final amplifier transistors in radios. And the way they work, so it's called field effect transistor, right? So the way they work is you put the control voltage on the gate, and you have this oxide layer here, which is an insulator. So that voltage changes the electric field in here, which allows more or less current to flow. That's why they call it a field effect transistor, because a voltage on the gate changes the current flow through the transistor. And like that's the question. Which of the following describes the construction of a MOSFET? Answer, the gate is separated from the channel. They call this the channel, because that's where the current flows, in the channel. The gate is separated from the channel with a thin insulating layer. That's the oxide layer. And, I mean, it's really kind of amazing. I mean, on a typical microprocessor chip now, there's millions of transistors, and they look like this, and sort of, not exactly, but sort of. It's just an amazing thing. Any questions about MOSFETs? Like I say, they're used a lot in final amplifier transistors now. They're final amplifiers. Now, this is kind of a busy slide. These are bipolar These are bipolar junction transistors. And the way they work is you put a little bit of base current into it, and you get a lot of collector current. And this explains the different regions of this chart here, okay? When you use this, and if you remember from the tech test, you can use this as a switch or as an amplifier. when you use it as a switch, what you do is you drive the transistor into saturation. By that I mean you put enough base current in so that the maximum amount of current flows through the transistor. Because at some point, here's the collector current, at some point, it's just not going to increase anymore. So that's the saturation point. The cutoff point is when you have little or no base current flowing. That's here, VBE is 0 or less. And when no base current flows, no collector current will flow. That's the cutoff region. That's this. IC approximately 0. Whoops. So in the saturation region, you have the max current. In the cutoff region, you have the minimum amount of current. And in between is the linear portion where it acts as an amplifier. So for each of these lines represents a different value of base current. And if you go up the graph here, then you figure out what the collector current is at which base current. And then you can figure out what the collector to emitter voltage is. But that's how it operates as an amplifier. And this is the equation here. Collector current equals the beta, or the gain of the transistor, times the base current. So, question, what are the stable operating points for a bipolar transistor used as a switch in a logic circuit? Answer, it's saturation and cutoff regions. So in the saturation region, you got the maximum current flowing through it. In the cutoff region, you have next to no current flowing through it. So it's a little bit busy. And if you got any questions about this, feel free to ask them, either now or later, whenever. All right. Almost done for tonight. Now, this is something many of you probably have never seen. This is actually a vacuum tube. And I chose this one, the 12AX7, because this one is actually still used a fair amount in audio amplifiers. So the audio nuts still think that tubes sound better than transistors. And this 12AX7 is still used a lot. What's inside a 12AX7 is actually two triodes. This is called a triode. It's two triodes. There's one here and one here. And it's called a triode because there's three active elements: the plate, the grid, and the cathode. This is the heater. It's not really considered an active element. The heater's there just to warm up the tube and cause the cathode to emit electrons. And if you put a voltage between the cathode and the plate, then electrons will flow from the cathode to the plate. And then you use this grid to control the amount of current that flows. By putting a more negative voltage on the grid, you get lower current flow. By putting a more positive, more current will flow. So this is the grid, or the answer to the question on the test is control grid. So question, which element of a triode vacuum tube is used to regulate the flow of electrons between cathode and plate? Answer, the control grid. Like I said, there's actually two triodes in this one tube. Now, while this is well and good, and we use triodes in a lot of circuits. One of the problems is that, you know, what you have here is actually a plate. You know, you got a bunch of metal, and this is a bunch of metal. Well, what happens is you actually get capacitance between here. If you don't take that capacitance into account, that could cause the tube circuit to malfunction, because all of a sudden you've got you know, AC current flowing from the plate back to the grid. So sometimes we put an extra element in here called the screen grid. And its purpose is to reduce this capacitance. They call it parasitic capacitance. So question, what is the primary purpose of a screen grid in a vacuum tube? Answer, reduce grid to plate capacitance. Here's a funny story about tubes. One time a guy called me up, a friend of mine, he knows I'm a ham radio operator. In fact, he was in one of my classes a long time ago. He calls me up, he says, Dan, I'm at the Ann Arbor Recycling Center. He says they've got 2 tubs of tubes here, and they want to know who they might want them. And so I asked him, I said, well, how many tubes do they have? He says, hey, I heard some mumbling in the background. He gets back on the line. He says they got about 200 here. So I said, well, how much do they want for them? I hear a little bit more mumbling in the background. And then he comes back on the line. He says, 10 cents each. Well, you do the math, that comes to 20 bucks. I said, well, I'll take them for 20 bucks. I hear a little bit more mumbling in the background. He says, I'll be there in 15 minutes. So about 15 minutes later, he rolls up, and sure enough, he's got these 2 big tubs of tubes in his car. And so now I got these in my basement. This is like, I don't know, probably close to 10 years ago. I've never used one, although I keep threatening to actually build a transmitter with these things. You can use this dual triode tube here to build a little amplifier, you know, or a little oscillator and an amplifier, sort of all in one. So you can build a single tube transmitter. So I keep threatening to do that. I haven't gotten around to that yet, but I got all these tubes. So if you ever need any tubes, just ask me first. Maybe I got one. If it's in the tub, I'll give them to you. And they said there was 200 of them. Well, I actually counted the number of tubes that was in one of the tubs, and there were over 200 in just the one tub. So I've got probably like 400 tubes in my basement. I got to get rid of them one of these days, though. Where was I going with that? I guess that's it. But yeah, so you know, some of the older equipment still uses tubes, and some hams like restoring that older equipment, and yeah, they're kind of fun. They do glow, and they smell different. The radio equipment with tubes in it smells different than radios that have just integrated circuits. So finally, there's a couple of questions here on batteries. I don't have any diagram for this, but question, what is an advantage of the low internal resistance of nickel cadmium batteries? So nickel cadmium are type, not so much used anymore, but they were popular at one time. What is an advantage of the low internal resistance of nickel cadmium batteries? Answer, high discharge current. So think about that. You know, if you had a battery and you're supplying, you know, some piece of equipment, this actually has an internal resistance, which you can model as a resistance in series with the battery. You want that to be low so that you can supply a high amount of current out of it. The higher that internal resistance, the lower amount of current you can supply. Question, what is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery? Answer, 10.5 volts. So lead acid batteries are still used a lot in, especially in portable equipment for portable operations. And you don't want to discharge them below that, or else they'll start malfunctioning. Any questions? All right. Well, thanks for sticking with me for the whole 2 hours. And we'll see you on Thursday. I'll send out another email saying what we're going to cover on Thursday. But basically, it's going to be the next, just the next chapter. And if you have any questions about any of this material, please feel free to contact me. That's my email address right there.
Thank you, Dan. Have a good night.
All right.
Thanks,
You
Dan.
too.
It was very good.
Yeah.
You.
Thanks. You said these recordings were going to go to YouTube somewhere?
Right. So just go to, I'll get it on there sometime tomorrow. Just go to YouTube and search for KB6NU and you'll find my channel. And I'll make a playlist for these online general class recordings.
Great. Thanks so much. Have a good night.
Thanks, Dan.
Yep. You
Thank
too.
you so much.
Thank you.
My pleasure.
Good night, Dan.
Thanks.